Hi everyone. Let's quickly take a look at some other graphs and charts. Dot plots. These are like histograms with thin classes, except that stacked dots replace the bars. Quick example, you can do this in an office or a classroom. An office has 6 employees. Cupcakes are brought to the office, and we count the number of cupcakes eaten by each employee. So a 1, a 0, so someone's on a diet, I guess. 3, someone's very hungry. 1, 0, and 1. All right. So basically, 2 people are on a diet. They don't eat any cupcakes. 3 people have exactly 1. No one has 2. Still, you want to put the 2 there because you do want to indicate the gap. And then 1 hungry person ate 3. So again, it's like a histogram with thin bars, and the dots replace the bars. Stem plots or stem and leaf plots. People don't use this in practice, but I actually did use these when I would grade, and I wanted to keep track of how well or poorly students were doing on like a 30-point question. Okay, and these resemble sideways histograms also. But unlike a histogram, you can actually recover the original data values. I mean, here for a dot plot, just bang, 2 zeros, 3 ones, and 1 3. But for histogram, like for the presidents, for example, right, you couldn't get back. You might know, for example, that there were 13 presidents in their early 50s, but I don't know, well, how many 50s, how many 51s, how many 52s. I cannot reconstruct the original raw data set, okay? But with a stem plot, you can. So here's the idea. And also, you can have the data values sorted, putting them in the correct order. All right. So for example, 9 students take a test. Their scores and points are as follows. This is not sorted yet. Stage 1 is to assign leaves to stems. So I'll put the scores up here, by the way. All right. So the stems, in this case, it corresponds to the tens place or the 1 0 over here. All right. Basically everything except the last digit. Really, this is designed for like test scores, integers. All right. Okay. So the lowest score is a 51. So the 5 here is your lowest stem. Someone did get 100, so a 1 0 is over here. All right. In stage 1, you go through. Okay, 77. Under the 70s, you put a 7. All right. 93. Under the 90s, you put a 3. 73. Under the 70s, you put a 3, and so forth. 2 people got 73, so you do have 2 3s in the 70s row. So the scores here in the 70s correspond to, this is like a modal class, 77, 73, 74, and 73. No one scored in the 60s, but like with the dot plot, do leave the gap there. Do put the 6 there. Do leave that blank space to the right because you want to indicate that gap. Already, if you turn your head around, I guess you could do that. Then you get kind of a histogram, sort of, right? All right. Okay. Now, so I might do this if I wanted to see how students were doing on a 30-point question as I was grading along the way. So I'd have like 0, 1, 2, 3. But technically, you're supposed to sort these leaves over here on the right. Okay. So when you sort the leaves in increasing order or non-decreasing order, right? Then notice you can read off the scores in sorted order. The 51, that's the lowest score. No one scored in the 60s. 2 people scored 73. There was a 74, a 77, an 82, an 85, a 93, and a 100. So you can actually get the sorted values. All right, time series graphs. Used for data that changes over time. Like, for example, the Dow Jones or the NASDAQ. Population, stock prices. Climate change. Concentration of carbon dioxide in the atmosphere. Up, 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 right? Exponential almost. For example, here's a time series graph for the US population in millions of people. In 1920, there were 106 million people, increasing like a J curve. What's that E word from your Algebra 2 class? exponential, right? In 2000, there were about 281 million people. And hey, in the year 2020, let's ask the Google. The Google says that the population of the US in 2019 was about 328 million. So for 2020, it's going to be about 328 or a bit more in millions of people. On the horizontal axis, you put the year. You don't want to start with 0. Okay, so let's start with 1920. Over here, well, there was no year 0, I guess. But anyway, US population in millions of people, starting with 0 and then 100 in millions of people, 200 and 300. If you put 2020 in here with this data point, you'll want to go to 400 as a tick number. Okay, well, again, 106 million at 1920, 132 million in 1940, 179 million in 1960, 227 million in 1980, 281 million in 2000. Bar graphs. Now we use histograms for quantitative data. Bar graphs are more for qualitative data, okay, consisting of categories. We sometimes call this categorical data. For example, political parties for the presidents. Remember, here was a frequency table, right? A bar graph, here's called a Pareto chart because on the left we have the most common party, and then we go in decreasing order by frequency, right? The 19, that's the modal class or category. There were 19 Republicans in red, appropriately, 16 Democrats in blue, 4 Whigs in green, that's over on the right, 6 others in gray. Again, in a Pareto chart, you're going in by decreasing frequency. So the 19 Republicans are first, then the 16 Democrats, 6 others, 4 Whigs, by decreasing order of frequency. Because remember, there's no natural order to this categorical or qualitative data. So the fair thing to use is the frequency. We go in decreasing, really non-increasing order. You could have ties. Again, the bars should be separated for qualitative data for these bar graphs. And you should use solid colors because you're not supposed to use things like stripes. Stripes could lead to the moire effect, which is like a vibrational effect to your eyes. You don't want that. You want solid colors. Unless you want to mislead people, make people dizzy. All right. Pie charts. And pie charts might be more objective than histograms or bar graphs because you can't mess as much with vertical axes or things like that. Pie charts are circular disks that represent both quantitative and qualitative data. All right. Possible values correspond to wedges of the pie. So we have here a frequency table for the parties, the political parties of the presidents. You could also do a relative frequency table if you use either this column or this column, if you use either this column or this column, right? Here's a pie chart. So for this pie chart, in red or pink, we have the Republicans, 19 Republicans. In red, that's about 42%. Okay, 16 Democrats, about 36% in blue. 6 others in gray, about 13%. And 4 Whigs in green, about 9%. Total is about, well, total should be 100%. Right? And the size of the central angles, the relative sizes of these wedges, depend on the relative frequencies. Again, pie charts might be a bit more objective because the math is more straightforward and you don't have a vertical axis to mess up. If you shrink or grow the circle, the disk, that doesn't really matter, right? All right. Until then.